Have you ever stopped to think about how massive computer networks, the ones that basically run our world, keep everything in sync? It's kind of a miracle they don't just drown in their own data. Today, we're going to pull back the curtain on the surprisingly clever, almost elegant logic that keeps these critical systems from talking in circles and creating total chaos.
So here's the puzzle, right? To make a network really, really reliable, you want lots of different paths for information to travel. It makes sense. If one road is closed, you can just take another. But wait a minute, doesn't that mean the same exact message could show up 2, 3, maybe even 4 times? How on earth does a system get all the benefits of being robust without creating a nightmare of repeated information? All right, we're going to break this all down into 5 simple parts. First, we'll dig into that redundancy puzzle. Then, we'll look at the brilliant solution, which is basically a clever ledger. We'll see it work in a real scenario, then witness the magic moment it stops a mistake. And finally, we'll talk about why this whole thing is so incredibly important.
Okay, section 1, the redundancy puzzle. So on one hand, to make a system dependable, you build in all these extra routes for data. That's called fault tolerance, and it's a very good thing. But on the other hand, it creates 2 huge potential problems. Data could get stuck bouncing around in an endless loop, or the exact same update gets sent over and over and over, just completely clogging up the whole network.
So that's the real challenge, isn't it? How do you get that rock-solid reliability without grinding everything to a halt? Well, the solution has this fantastic name, propagation dampening. It's basically a way to quiet the echo, to make sure a message is heard exactly once by every server that needs to hear it, and not a single time more.
So how in the world does this propagation dampening actually work? Well, the solution isn't some brute force, complicated mess. It's actually incredibly elegant, and at the very heart of it is something called the up-to-dateness vector. Honestly, the best way to think about it is like a small, smart ledger, or maybe a personal scorecard that every single server keeps for itself.
And what's so cool about this is just how simple it is. The up-to-dateness vector is, well, it's just a list. That's it. Each server keeps a little running tally that says, okay, here's the version number of the last update I got from server A, here's the last one I got from server B, and so on. It's just a simple memory of what it's already heard and who it heard it from. Let's take a look at what one of these ledgers actually looks like. So imagine this is the scorecard for a server we'll call DCB. It's really simple. It's just saying, hey, the last change I saw that originally came from DCA was version 2. And that version number? It's called a USN, which stands for Update Sequence Number. This little table right here is the key to this entire brilliant system.
All right, let's put this whole thing into motion. Let's see what happens during a totally normal, everyday update. It actually helps if you imagine these servers as people in a group chat, all trying to make sure they have the latest piece of news.
Just a real quick bit of lingo here. The person that's actually doing the talking on each server is a process called the Directory System Agent, or DSA. You really don't have to remember that. Just think of the DSA as the little worker bee on the server that's handling all this back and forth communication we're about to watch.
Okay, let's follow the data. First, someone changes a password on server DCA. That change gets stamped with the new version number, 3. Simple enough. Next, server DCB pings DCA and basically asks, hey, got anything new for me? Oh, and by the way, here's my scorecard of what I've seen so far. So DCA looks at B's scorecard and sees that the last update B got from it was version 2. Since this new update is version 3, and hey, 3 is greater than 2, DCA sends the change. It's all perfectly logical.
But, that was the easy, straightforward scenario. This is where the real magic happens. This is the dampening effect. What if, because of those extra network paths we talked about, what if DCB had already gotten that password update from a different server, like DCC?
And here it is. This is the aha moment. On the left, that's the scenario we just saw. DCB has a version 2, the new update is version 3, so DCA sends it, no problem. But look at the right. In this case, DCB has already heard about this change from someone else, so its scorecard for updates from DCA is already at version 3. Now, when it asks DCA for updates, DCA does its simple check. It compares its new update, version 3, to what B already has, which is also version 3. So, is 3 greater than 3? Nope. And so DCA sends nothing. The echo is silenced. The propagation is dampened. It really is that simple.
So, let's just zoom out for a second and appreciate what this simple piece of logic actually does. This isn't just some neat little computer science trick. It's a fundamental principle that allows these massive, globe-spanning, reliable networks to even exist in the first place.
So what does this get us? Well, it gives us that perfect balance we were looking for, all the fault tolerance we get from having multiple paths, but with none of the inefficiency from repeated data. This one little trick dramatically cuts down network traffic, which makes everything faster for everyone. It completely, totally prevents those catastrophic data loops we worried about. And at the end of the day, this simple logic is what ensures the stability of these huge systems that thousands, even millions of us rely on every single day.
And that kind of leaves us with a final thought, doesn't it? This entire, incredibly effective system, it all boils down to a simple question. Is this number bigger than that number? It really makes you wonder, what other beautiful, elegant, totally invisible bits of logic are working silently in the background every second of every day just to keep our incredibly complex digital world from falling apart? Thanks for digging into this with me.